My name is Blanca Castells and I come from the Technical University of Madrid, and I'm gonna present the study that me and my team have carried out, which is called New Methodology for Determining Initial Temperature of Combustion Related to Gas Emission. In this presentation I will start with a brief introduction about the importance of this new methodology. Afterwards I will talk about the materials and methods that we have used to carry out this methodology. And I will present the results, a short discussion, and finally I will end up with the conclusions of the job. Several industrial accidents happen because self-ignition process. The self-ignition process is it's a process in which the substance begins its combustion without any external ignition source. So the very beginning of the process is a self-heating of the material that can belong to a combustion. Different methodologies have been used in the past years to study the self-heating process, as for example TGA, thermogravimetrical analysis, DSC, differential scanning calorimetry, HRR, heating release rate. But I'm gonna use a different, not so common methodology, which is through gas emission, gas related to combustion emission. Why? Because it's cheap. It's really cheap, and if we can make it work properly, we could use this methodology to detect those processes without wasting money in really expensive equipment. This methodology was presented a few years ago, but what I have carried out is a new evaluation method, because the previous method was really, let's say, constrained, and it was not useful for industries. The materials that we have used are 6 different samples, which include 2 different charcoals, 3 different biomasses, pine shaving, wheat straw, and olive pellets, and also dog food. We have used those samples because they are always stored in huge piles, and they are transported in huge quantities, in huge amounts, so they have a tendency to do this self-ignition process. And in the table you can see the particle size. We have used 3 different particle sizes for the 2 charcoals, and 2 different particle size for the other samples. And the moisture content. One of the charcoals has a lower moisture content, but it's not really relevant for the study. This is just a screening. For the test that we have carried out, the first one was the thermogravimetric analysis. Probably you would know, but I'm going to explain it in a brief way. In this study, what we do is we heat a sample at the heating rate. In this case was 5 Kelvin per minute, and we measure all the time the weight loss. That allows us to know where the induction temperature, which is called IT there, I don't know that, which is the temperature at which the reaction of combustion really accelerates, and then the combustion increases. But the very beginning of the combustion, it's called the ECT there. And it's the temperature corresponds when we have the whole mass percentage. If we take out if we subtract the moisture content, what we have is the full the real mass that it's gonna combust. So we also have the 3 different states: the water evaporization, the volatilization process that ends with the maximum loss weight temperature, and the characterization. As I said, the really parameter that we're going to use is this ICT. For the gas emission analysis, what we have done is take the sample and put it inside a cubic cell, and put it inside a sealed cylindrical container with a thermocouple inside the sample, and a pump that can extract the gases from this container. We put everything inside an isothermal oven, and we heat it from 40 degrees to 200 degrees. And every 20 degrees, we just activate the suction pump and we take the gas in those tubular bags. Afterwards, we take the tubular bags and put it in a gas analyzer, and we get the CO and CO2 emissions at each temperature. What we can do with that is calculate the relative difference, which is explains with those formulas, and the relative percentage. It allows us to, when the relative percentage is greater than 20%, we call it the critical interval. That's if we plot the emissions along temperature from 40 to 200 degrees, we got a curve like this, and the critical interval is here. Here's where the relative percentage is greater than 20%. So what we have done is take the previous points of this critical interval and the following ones and make two moving average lines in order to obtain the crossing point that it's called EIT, in initial emission temperature. So the results of those of the TG and the gas emission evaluation are shown in this table. But the most interesting thing is the comparison between both results. In order to detect the very beginning of the combustion, we have used the carbon monoxide emissions, because they are always produced before the carbon dioxide emissions. And we have compared the average of those to the ICT, which would be like the real moment of the beginning of the combustion, and calculate the relative error. Of course, we can see that this sample didn't work. But with all the other samples, the results using the EIT was pretty accurate. Even more, if we compare it with the previous methodology and we calculate the relative error using the methodology that was used previously. So what can we conclude from this? This new methodology is stable enough and gives a result that really approximates the real combustion parameter. So it can be used for early detection of this self-heating process that can be used to define safety measures applicable to storage and transport activities. Further studies need to be carried out, because we have to improve this in order to get better results of relative error. But this is a very good first step to achieve this new methodology. So, thank you for your attention. If you have any questions, just please contact me.
Thank you, Blanca.